Hello, good afternoon, everyone. Let's get started. This week we're going to be doing lecture 2, which is about macromolecules. And again, hopefully you have had some time to watch the lecture recordings for lecture number 2. It will make much more sense if you have watched that already, and then come to the tutorial. So let's go through these questions. First question. List 5 major elements found in living things. So we know that the universe is made up of many different kinds of elements, right? You can find all these elements on a periodic table. There are over 100 of these elements. But in terms of living organisms, like humans, for example, there are 5 key elements that are found within a living system. And examples of these are carbon, hydrogen, nitrogen. They are in no particular order, okay? Oxygen. And what's the last one? Anybody remember what the last one might be? I ask because that's the one that usually people forget about. Carbon, hydrogen, nitrogen, oxygen, and one last one.
Phosphorus.
Phosphorus, that's right, thank you. Phosphorus. So that makes up the majority of the elements within a living organism. Now, there are also trace elements that exist within our body. Trace elements are elements that are required in small quantity. Okay, you don't need a lot of them. You just need a little bit. In fact, if you have too much, usually that will cause some kind of conditions. And if you don't have enough, you also might have a little bit of a problem with it as well. So we just need to have the right amount of trace elements in our body. What are some examples of trace element? Anybody?
Calcium.
Calcium, that's absolutely correct. And we need
Magnesium.
calcium. Yeah, magnesium, right.
Iodine.
Iodine, yeah. And just one more.
Zinc.
Zinc. Yeah, so these are the examples that were given in the PowerPoint slides, right? Okay, you probably know some other ones like iron. Okay, you need iron for transporting oxygen. If you're low in iron, you might get anemia, right? Calcium is important not only for bones, but we also need calcium for muscle contraction, for communication between neurons. Not having enough calcium could cause weakening of the bones, right? Osteoporosis, but it could also cause muscle weakness. Okay? Magnesium also needed for muscle contraction. Iodine, we use it to make hormones, and zinc is important for your immune system. Okay? So these are some examples of trace elements that we need in the body. We then talked about the difference between ionic compound and molecular compound. This is probably something that you are learning in chemistry class as well, but we do need to know the difference for the macromolecules. So let's just go through them briefly. For ionic compound, the elements that are involved would be metal and non-metal. Okay. I don't know if you learned this yet in your chemistry class, but if you think about your periodic table, right, that looks something like this. There is if you look at your periodic table, there is like a staircase that goes down, right? So things that are left of the staircase, they are typically metal, and then those to the right of the staircase, those are the non-metal. So the ionic compound involves taking a metal and you combine it chemically with a non-metal. The type of bond that you form in ionic compound is called ionic bond. Ionic bond, which involves the transfer of electron. It could be more than one, from the metal to the non-metal. Okay, so for reasons we're not going to go into, metals, they don't really like electrons. They love to give them away. And for non-metals, they love to take on electrons. So they are a perfect pair. The metal and the non-metal will come together and you transfer the electron, forming an ionic bond. Okay. So before we fill in more, let's just contrast it with molecular compound over here. A molecular compound involves the bonding between non-metals. Okay, so only non-metals, like carbon dioxide, for example. It's entirely made up of non-metals. And the kind of bond that you have in molecular compound is what we call a covalent bond. Covalent bond. In covalent bond, instead of transferring the electron, yeah, Ezra, you have a question? Go ahead, please.
Yes, thank you. Ms. Vincent, can you please post these answers as a PDF in the homepage or news? Because sometimes I don't need to listen to the record.
I do post them though, right? Did you okay, well, thanks for raising this
couldn't
point.
find the last one. I don't know.
Yeah. Let me show the whole class, because probably other people don't know where to find them as well. Okay, just give me 1 second. Where are we? Okay, so after each class,
Okay.
if you guys go to the course homepage, I usually would give you a debrief. Okay, so
Okay.
a couple of things. There is the tutorial archive. So if you click on that, it will take you to the recording. So that's like the whole session being recorded, right? Okay, and I hear what you're saying, right? Rather than watching the recording, you just want to, look at the answers, right? Then you would go to over here, right? You said you can find full study guide solution here. So you click on that, and then you will have it, right? So far I only post the first study guide, right? Because that's all we've done. But after today's session, I will post the answer for lecture 2, right? Okay.
Yeah, you mean this is the answer, like the PDF for the last.
Yeah. I mean, it's not PDF, but it's like a Word document, but then it has all the answers, right?
Thank you so much.
Okay, yeah, no problem. So you probably want to bookmark those 2 places because I'm gonna keep on adding things to it as we go on. All right. So yeah, moving on. Where was I? Yeah, the type of bonds that are being formed, right, in the molecular compound, that's the covalent bond. And in covalent bond, rather than having a transfer of electron, we have sharing of electrons. Sharing of electrons. And you might share more than one. And it's sharing of electrons between the non-metals. Okay. Now, what about the state at room temperature? What kind of state do these ionic compounds exist in at room temperature? Are they solid, liquid, gas, combination of these things? What are they?
I just guess it's a liquid.
Okay, yeah, good guess, good guess. The ionic compound is really strong, the bond holding them, and so it takes a lot of energy to cause them to become liquid and gas. For the most part, ionic compounds are solid at room temperature. Yeah, that's okay. It was a good try. You know what? I just want to mention another thing. Since we are talking about this, give me 1 second. Let me just share my screen with you guys again. Share screen number 1. So I actually got a lot of email on Monday saying, the link doesn't work. Where is the class? Remember, on Monday, you were supposed to watch the lecture recordings on your own, right? And, I did a quick check here for this lecture, right? Like only less than half of you have watched the recording. Like if I click in, I can see who actually did it, right? And then of the half of you who watched it, only half of the half continue to watch part 2 and part 3, right? So I cannot stress the importance of watching the videos. If you just come to the tutorial is not gonna fully cover everything that are in the videos, right? The tutorial serves as a way to summarize the lecture, right? We do some practice questions and whatnot, but like half of the learning you have to do on your own, right? And that's the nature of online delivery. Okay, do you guys understand what I mean by that, right? Like if you look at the schedule, I would tell you, right? Next Monday will be asynchronous learning, and then you have to watch these recording. You click on it, and it will take you to the recording page, right? So for next week, you will have to watch the recording for lecture 3. Okay? So I'm just saying, if you didn't watch the recording and you come to the just for the tutorial, it will not be sufficient for you to do well in the course. Okay, you must do a combination of both. I hope that makes sense. Okay, and if you're not sure where to find things, please feel free to email me, and I'll be happy to tell you to redirect you. Okay. All right, so that would be solid at room temperature. An example of ionic compound would be NaCl. Right, that would be table salt. Let's talk about molecular compounds. Now, the bond is not as strong in molecular compound, and so they could exist as solid, liquid, or gas. Right? Any of them would be possible. Does anyone have examples of molecular compounds by any chance?
Water, like a H2.
Yeah, H2O. That's correct.
Yes.
Yeah, so that would be the liquid example for water. Anything else? For solid, for gas, perhaps. Sort of mentioned a gas earlier. That's okay. So we have carbon dioxide, for example, for gas. Carbon dioxide. Okay, and for something that's solid, maybe like C6H12O6, right? Like sugar, right? Okay. Glucose. So these are examples of molecular compounds. They are made up of entirely just non-metals. So there you have it. Comparison between ionic and molecular compound. Okay, next we have a water molecule here. Water molecule is made up of 2 hydrogen and 1 oxygen. And as we just discussed, this is molecular compound. So in molecular compound, we have a sharing of electrons. So this bond here, that's a covalent bond. And we have a sharing of electrons. Now, the electrons are being shared, but they are not necessarily being shared equally. Okay, the oxygen actually has a higher attraction for electrons, and so the oxygen will pull the electrons towards itself and kind of hang on to it more than the hydrogen would. Okay, so because of that attraction of the electron, it will cause the oxygen to become slightly negative. Okay, slightly negative. And then for the hydrogen, because the electron is being pulled away towards the hydrogen, they will become slightly positive. Okay, so that's what it means by the polarity of water. Okay, so I'm just gonna write a quick note here. Due to uneven.
Can you come again?
Sorry?
Yes, can you explain this plus and negative again?
Sure. So that's what I'm writing right now, right? So due to uneven sharing of electrons, the oxygen atom has higher attraction for electrons, making it slightly more negative. Okay. So, if the electrons are being shared evenly, then that means, 50-50, right? Half and half. But if it's uneven sharing, then the oxygen kind of gets to hold on to the electrons more than the hydrogen. And of course, electron gives it a slightly negative charge, right? As an analogy is like this, okay? Like I bought this toy for my kids, and I told them you guys have to share. But then the older one, it's like hogging it all the time, right? So, they are sharing, but then the older one gets to play with it, more than the younger one. So it's uneven sharing. It's not 50-50, right? And that's kind of what's happening here. The oxygen is holding on to the electron more than the hydrogen, and that causes it to become more negative. Okay, when a molecule is slightly more negative in one side than the other side, that's what causes it to become polar. Okay, so overall, the molecule is still neutral. There are no extra electrons or missing electron, but it's polar because part of it is slightly negative, another part is slightly positive. So what that means is if I take a water molecule and I put it next to another water molecule like this, and maybe I'll just draw another one here. Okay. The oxygen that is slightly negative will be attracted to the slightly positive part of the hydrogen, right? And that will create a little bit of an interaction, kind of like a magnet, right? The opposite poles attract each other, like that, like that. Right? So these interaction is called hydrogen bonds. Okay, that's the implication of water molecule being polar. Does that answer your question? Was it Victoria, I think, or do you have a follow-up question?
It's fine.
Yeah, okay, Victoria. Sorry, yeah, Victoria. Okay, moving on. Use a diagram to explain how ionic compounds such as sodium chloride are soluble in water. Okay, so you might remember ionic compound involves the transfer of electron from the metal to the non-metal. So in this case, the sodium is the metal, which will be losing the electron. Okay, so let's draw the sodium here, and then give it a positive charge because it has lost the electron, right? And we will draw the chlorine over here using a different color. And chlorine is bigger than sodium if you look at the periodic table. And after picking up the electron, it will become negative, right? And so what happens is water molecule will surround each of these differently. Okay? Do you think it is the oxygen that surrounds the sodium, or is it the hydrogen portion that surrounds the sodium? What do you guys think?
I think it's the hydrogen.
It's the hydrogen, okay? And you know what? Let's do a poll and see what everybody thinks. We'll launch a poll for you. Oops. Okay, so my question is, if you think about water molecule H2O, which part will surround the Na+? Is it A, the oxygen part, or is it B, the hydrogen part? Okay, so please choose something. If you're not sure, you can choose C. All right, anyone else wants to select an answer before I close the poll? Okay, well, thank you for those of you who have participated. Well, opposite attracts each other, right? So the oxygen is slightly negative and the hydrogen, they're slightly positive. So the positive sodium will be surrounded by the oxygen, okay, because that's the part that is negative. Okay, like so.
So the answer is A, right?
The answer is A, that's correct. Okay. But more importantly, do you understand why, right? Like this is slightly negative, right? Opposite are attracted, right? Okay, just like North Pole attracts South Pole, positive attracts negative.
Yes.
And over here we have the chlorine, and that's going to be surrounded by the hydrogen this time. Okay. So anytime the ionic compound is put into water, the water will separate the metal ion from the non-metal ion, and it allows it to dissolve. Not everything can dissolve in water. What's the term that we use to call things that cannot be dissolved in water, cannot mix with water? What's the term that we use?
Hydrophobic.
Hydrophobic, that is correct, right? So things like ionic compound, these are hydrophilic, right? Hydrophilic. They are able to dissolve in water. Dissolves in water. Okay, if they're not able to dissolve in water, as the student mentioned, it would be hydrophobic. Okay, all this is in the lecture notes, the PowerPoints. Okay, next question. We are going to compare acid with base. Okay, so when you have a solution, a liquid solution, you can test whether it is acidic or whether it is basic. Okay, so by definition, something is acidic if it has if it produces hydrogen ion or H plus when dissolved in water. Okay, and for base, it's something that produces OH minus when dissolved in water. Okay. So we use something called pH to determine whether something is acidic or basic. The pH scale, for practical reasons, we will say it goes from 1 to 14 generally. Right? If the pH is less than 7, then we'll say the solution is acidic. If, on the other hand, it is greater than 7, then we'll call it basic. If it's right at 7, right, if pH equals to 7, then it is going to be called neutral. Yep, thank you. Okay, so properties of acid. Okay, first of all, can anybody give me some examples of acids? Like everyday lives that you encounter, acids at your home.
Lime juice.
Yeah, sure. Lime juice. Anything else?
Tomatoes.
Tomatoes. Anything else? Something that's not juice, maybe. Anything else that's acidic? You probably have it in your kitchen.
Vinegar.
Vinegar, that's the one I'm looking for. Thank you. Okay, so if you think about these things, right, like they're sour, right? They are corrosive. Okay, so these are some properties of acid, right? We also have acid in our body, right? Do you know that? Which organ had? Sorry, what was it, Ezra?
Buttermilk.
Milk is slightly acidic, but that's not what I was thinking. Good try though. Which organ has? Sorry.
The lactic acid, I mean.
Oh, the
mean,
lactic acid.
Buttermilk.
I see what you mean. Yeah. If you exercise a lot, you know, and then push your muscle beyond the normal capacity, you might build up lactic acid. But I was thinking about something in your stomach, right? We have acid in the stomach. Someone said gastric acid. That would be correct. And that one is hydrochloric acid. Okay, HCl.
Also grapefruit.
Yeah, grapefruit. Yeah, any kind of citrus, right? Would be acidic. Very good. Okay, basic stuff. Things that are on the other end of the scale. Any example of base, please? Anyone?
Sorry, excuse me. You were saying about acid in our body. Is it the HCl?
Yes, actually, it's in your stomach. It's stomach acid. Okay, so it helps us digest our food. Okay, I can spell it out for you. Hydrochloric acid. There you go. Base. Anything? Again, in your home.
Soap.
Soap. That's right. Soap. Soap is pretty basic.
Toothpaste.
What's that again? Sorry.
Toothpaste.
Toothpaste. Yes. Toothpaste. It's interesting.
Or any kind of bleach, like.
Yeah, bleach. Right. Very good. All these things are basic. Yeah, well, I mean, we don't really eat these things. You shouldn't. Anything that we can eat that's actually basic. Used for baking, for example.
Baking soda.
Baking soda. That's right. When I say baking, it kind of gave it away, right? So all these things are basic, and if you taste any of these, you definitely should not taste bleach. But if you accidentally have some soap going into your mouth, if you add a little bit too much baking soda into your muffins, they will turn out to be a little bit bitter, right? So bitter. Toothpaste is not bitter because they add some sodium fluoride in it, and that makes it a little bit salty. The sodium fluoride helps prevents cavity. Bitter, they are also corrosive. Okay, if you pour bleach, if you put metal into bleach and come look at it later on, it will get corrode. All right, so there you go. Those are the examples. Excuse me. All right, next, list 4 types of macromolecules. The molecules are like, when you combine atoms together, you get molecules. Water is a molecule, but it's really small. It only has like 3 atoms in it, right? 2 hydrogen and 1 oxygen. When we talk about macromolecules, these are molecules that have a lot of atoms in it, like sometimes thousands of atoms in it. Okay, and there are 4 main types of macromolecules that are found in the body. We have carbohydrates.
We have protein.
We have proteins, that's right.
Nucleic acid and lipid.
Very good. Nucleic acid and lipid. Those are the main ones, okay, that we're gonna look at. Now, what is so common about these macromolecules? Well, each of these macromolecules are they are polymers, okay? And the polymers are basically really long chains of molecules that are made up of repeating units, which we call monomers. So in this diagram here, the stuff on the left, the individual units, okay, these represent monomers. Okay, you can think of the polymer as a long train. Okay, and the train are made up of individual carts. The carts might be the same if you ever see a GO train, right? Each cart is identical, but they might not be the same, right? If you ever get stopped at a rail crossing and one of those long CN rail train pass by, each cart is kind of different, right? But regardless, the whole train is made up of repeating units of these carts. So the carts are like the monomers, and we can connect them together to form the polymer. Every time we link the monomers together, right, we have to use a specific process to do that. And the name of the process is called dehydration. Dehydration synthesis or condensation. Condensation reaction. We can also break the polymers to get the monomers back. And what is the name of that process? Does anybody remember?
Hydrolysis.
Yeah, so very good. 4 people mentioned hydrolysis at the same time. That's lovely. So we add the water and we break the chain. That's what lysis means, right? So how, what would be a concrete example of this happening in real life, right? So you might consume some proteins during lunch, okay? If you had some meat, that's proteins in there. If you had some cheese, that's protein. Or if you had beans, right, that also is proteins. So those proteins, when you eat them, when you ingest them, consume them, they exist as polymer. Okay, and then your digestive system will break down the polymers into the individual building blocks of the proteins. So in the example of proteins, those would be amino acids. Okay, so your body would use water to break them, and then now you get these amino acids. The amino acids can get absorbed into your cells, and now your cells can take these amino acids and build proteins that your body needs. Okay, maybe you need to use make proteins to repair your muscle. Okay, maybe you need to make proteins for new hormones. So your cells will take these individual building blocks and then make it into a polymer. Okay, so you get the raw material from your food source, and then you use the raw material to build things that you actually need in the body. Okay, so that's polymer right here, and that's monomer. Okay, so I just want to refresh your memory about the dehydration synthesis. Okay, so let's say we have one molecule here that looks like a hexagon, right? So like if you watch the lecture recording, you would know like the glucose looks like a hexagon, right? So there might be like an OH here, and then we might have another hexagon here that represent another molecule, and then there's another OH here. And if I want to connect them together using dehydration synthesis, right? Dehydration means to remove a water, right? So you can take away the OH from one of them, you can take away a H from another. So when you remove these things from the molecule, you will end up getting the H2O. Okay? And then what you will end up doing is creating a bond that links them together. Okay, so you see, right, the O here is now going to make a new connection to the other molecule, and now they are connected. Right, so these are covalent bonds. Right, all these involve sharing of electron. Do you guys understand?
Yes, and I have a question, Vincent,
Yeah,
please.
please
For
go
the
ahead.
for the upcoming quizzes and tests, do we have to found question like this, label the diagram below and something like that? And do we have to draw like structure?
No drawing is needed for the quiz. And there might be labeling, but the labeling, I would give you a diagram, and then maybe I would do this. Okay, maybe I'll call this M, and then I ask you, what is the label for M, and then you would choose the appropriate label. Does that make sense?
So I need just to fill the with the polymer on the right side and hydrolysis down and something like that.
Yeah, that could be it, but then like you wouldn't have to write out the words necessarily, right? Like I would point to this thing and ask you, what is that called? And then you would just choose the choice, right? Like A, B, C, D, right?
Polymer. Okay.
Yeah. Okay.
Okay,
Exactly.
thank you.
Yeah, and then there, since you brought up the quiz, I actually post the information about the quiz online
I saw it. Yeah.
as well, right? Yeah, okay, so
In
for
the
those of you who,
homepage.
that's right. In case you guys didn't see that, if you go to the eCentennial homepage, right, there it is. So on the day of the quiz, which is next Monday, you will. Is it next Monday? Yeah, it's next Monday. Wait, did I get it right?
And is it 1 hour?
No. The quiz. Okay, I'll put the time limit as well. So you will click on the link here, and then it will take you to the quiz page, right?
Yes.
Over here, and then it will tell you how much time it is. I forgot to include that information. So it will be 45 minutes. Okay, 45 minutes.
Okay.
I probably should include that right now for you guys. Sorry.
Thank you.
Yeah, time limit 45 minutes. Okay. There you go. And you would have access to the quiz from 6 a.m. to midnight. Okay. But remember, once you start the quiz, you cannot stop it, right? Okay, you cannot close the browser and come back later. The timer does not stop. Okay, so make sure you find a good time to do it. Okay, and it will cover lecture 1 and lecture 2. There will be 16 multiple choice questions, 5 multi-select. These are questions that have multiple correct answers. And then there will be 2 short answer questions. So these questions require you to type in answers. Okay. You don't have to write a paragraph. Okay, it's nothing like that. These are very, you can answer them with 1 or 2 sentences. All right, but you must do it in your own words. Okay, if I see some answers that looks like you are just copying directly from the notes, or like you got it from the internet or something like that, then you might receive a penalty for it. And then you might ask, how would you know if I come up with it myself or if it's on the internet? Yeah, I usually have pretty good judgment on this. Okay, like I've been doing this for like 15 years, right? So like when I see an answer, I usually will be able to tell whether it's an answer that you make up or like if it's copied from somewhere. Okay, and if there is like discrepancy, we can discuss about it later. But general rule is you answer the question yourself. Okay, don't try to copy things from another source. That's my point. Okay.
And is it direct submission? I mean, once we finish the quiz.
Yeah. Once you
have to
submit,
click on
once you finish the
submit and
quiz, on the
that's it?
last page, there is a button that says submit, and you click on it, and then it will be, I'll receive it. Okay.
Okay, thank you.
Yeah. If you need practice with the multi-select questions, you can check out the self quiz. There are some examples there as well. All right. Yeah. Thank you. If you need further clarification, please do let me know. Okay. So every time you connect 2 monomers together, you need to remove a water molecule, right? And so here, let's take a look. We have 1, 2, 3, 4, 5, 6, 7, 8 monomers, and we connect all of them together. So how many water molecules would be removed in this case to form a long chain like that? If we need to connect 8 of these together, how many water molecules do we need to remove?
Two.
7.
7, that's right. Okay.
7.
So when I connect 1 and 2, right, that bond requires 1 water molecule to be removed, 2nd water molecule, 3rd, 4th, 5th, 6th, 7. Okay, so every time you form a bond, you need to take away a water molecule. Okay, let's do some polls. All right, you should be able to answer this if you had been paying attention. Go ahead, please. Okay, anyone else? All right. So that's the result. And the correct answer is uneven distribution of electrons, right? Because the oxygen is pulling the electron towards itself more compared to the hydrogen. That's why it becomes slightly negative. Now, it is true that the molecule, the polar molecule, the hydrogen, it's slightly positive, but it doesn't have a positive charge. Okay, to have a positive charge, it means you actually have to lose an electron, right? But it didn't lose the electron. It was sharing with oxygen, but it just didn't get to hang on to it as often. So it's just slightly positively charged, not a full positive charge. Okay, so the correct answer is C. It has uneven distribution of electron. Let's take a look at this next one right here. Okay, so we have a hexagon here, we have a pentagon here, and if we want to connect them together, we're gonna take away the OH here, and then we're gonna take away the H, and we will make a connection. So we will have a hexagon with an O, connected to a pentagon. So that would be the correct answer. All right. It's not D because D is hexagon, right? Hexagon and pentagon. It's not A because it's missing an O. Right. So hopefully that makes sense.
Vincent, how about the C? I was confused with the B and C.
Because C is pentagon and pentagon, right? So like, you know, it's a hexagon with a pentagon. So it wouldn't be the same shape, right? Does that make sense?
Oh,
Yeah.
okay.
Mm-hmm.
Thank you.
No problem. All right. Now we're gonna move on to the carbohydrates, right? So carbohydrates, the elements.
The answer is C for the previous question.
The answer is B. The answer is B.
C, right?
B.
Oh,
B. The hexagon is like over here, right? This part corresponds to that, and then the pentagon corresponds to that, right?
Yes, yes.
Yeah. All right. Okay. Let's take a look at carbohydrates. All right. So for carbohydrates, the elements that are found in the carbohydrates include carbon, hydrogen, and oxygen. Right. The monomers, the building blocks that we have for carbohydrates, they are all called monosaccharide, right? Monosaccharides, which means single sugar. And there are 3 monosaccharides that we talked about in class. The first one is glucose. What's another one? Does anybody remember?
Fructose.
Fructose. Good. And just one more.
Sucralose.
Sorry? I just didn't hear that. Sorry.
Sucrose.
That should be
Sucrose
galactose.
is it's a combined one. So not quite sucrose, but yes, galactose.
Galactose.
That's
Is it
another one.
galactose?
Yeah, galactose. That's right. Okay. So these are the different monosaccharides, single sugar. Now, what is the biological function for carbohydrates? For the most part, the carbohydrates for humans, anyways, is for energy, right? Use. Used for energy. Okay. In plants and in humans, we can store them as well. Storage form of energy. Okay. When we need it, we can burn them off and create energy. We can also store them. And in some cases, for some organisms, they are useful for structural support. Structural support. Okay. Like the fibers in plants, that's made up of carbohydrates. The shells of crabs, lobsters, insects, those are made up of carbohydrates, and it provides them with structural support. Okay, using the diagram below, show how a bond is formed between 2 glucose molecules. So we have glucose molecule here, right? That's what the hexagon is, right? Like in our diagram earlier, right? I would never ask you to identify these things or ask you to draw them, okay? But if you try to combine this glucose with this glucose, what would happen is, if you take a look at the notes, you're gonna take an H here, you're gonna take an OH here, and then you can take it out and it become H2O, and then it will create a bond, right? Create a bond. Okay, so for simplicity, we're just gonna draw the hexagon like we did, and then we're gonna have an O that connects them. Okay, so this again is dehydration. Dehydration synthesis. Okay. And you're gonna have a new bond that connects them. Okay. Well, technically, it's supposed to. You're supposed to take the H
Connects
from.
with the other.
from-
Exactly. I wanted to ask.
Sorry, what's that? I didn't hear you. Sorry.
I was about to ask if that's the, if you connect the OH to the H or the OH to the OH.
You would connect this O, right, to the carbon actually right here.
Yeah.
But it's not super important that you know which one to connect. The point here is you have to remove a water molecule, and in doing so you form a new bond. Okay. New bond. Okay, so that's that. Now, we were just saying there are 3 different types of monosaccharides, right? So we can combine them in different combinations. excuse me, you can combine them in different combinations. For example, as we did here, we took a glucose molecule and we combine it with another glucose molecule, and we end up having something called maltose. If you take a look at the ingredient list of your chocolate bar, you will almost always find maltose in there. Okay. How do you get glucose? Sucrose. You will take glucose
Glucose plus fructose.
plus fructose. That's right.
Fructose.
That's how you get sucrose. Now, sucrose is your kitchen sugar. Okay, the regular sugar that we use for cooking, for baking, and that you find in convenience stores. That's sucrose. Okay, we don't actually have glucose readily available, at home or like even at the store, right? The glucose actually exists as kind of like a syrup form. Okay, and then we use sucrose mostly for cooking. And then lastly, lactose, which is found in dairy products, milk, cheese, ice cream. That would be glucose plus.
Galactose.
Yep, galactose. Very good. Okay. So all these things here, the stuff that are on the left, right? These things, just want to reiterate, these are monosaccharides, single sugar. Monosaccharide. It's one word. Okay, let's try to fit it in here. Mono, S-A-C-C-H-A-R-I-D-E. Monosaccharide. And when you combine the monosaccharides together in various combinations, you end up having these double sugars that are linked together, and we call these disaccharide. Okay, disaccharide, double sugar. And you can repeat this process. You can keep on adding more glucose if you want, and eventually you will end up with a very long chain, and we would call that chain a polysaccharide. Okay, polysaccharide. Does anybody have any question before I move on? Please ask.
Thanks.
Okay. Speaking of polysaccharides, these are 4 examples that we talked about in the lecture. So let's go through each one of them and refresh our memory. We have starch. Where can we find starch? We can find starch in plants, for example. Plants. So plants, they use the sunlight to make sugar, and then they make a lot during the summer, for example, and then they will store it for cloudy days, for the winter, for example. And where do plants store their starch? Does anybody know?
In the roots.
In the roots, that's right, in the roots. So of course we eat the roots of many plants, and we enjoy the starch, right? We get the energy by eating the roots, right? What are some examples of roots that we eat?
Cassava.
Did you say cassava?
Potatoes.
Yeah, cassava. Yeah. Another one?
Yam.
Yam. Yeah. Potatoes, right?
Potatoes.
Rice.
Yeah, not rice though. Rice is a grain, right? But the roots would have to be like, underground, right? So like carrot is another example. Okay. So the main biological function for starch is that it acts as the storage form of energy for plants. Okay, we don't have starch in our body. Okay, you have to remember that. We eat them, but that's about it. We don't make starch. But it doesn't mean we cannot store energy. Okay, we store them as glycogen. Right? So we will find them in animals, not just humans. Other animals have glycogen as well. And which part of the body do we store the glycogen in?
The muscle.
The muscle, yeah. As well as
Liver.
liver. That's correct. Thank you. So if we consume more than what we need, the extra sugar will be stored in the liver and the muscle as glycogen. So if you skip a meal, if you are fasting, for example, then your body would run on these energy reserve. Okay, you will take the carbohydrates from the glycogen and you will burn those as fuel instead. Okay, so that would be the storage form of energy for animals, including humans. Cellulose, that is found in plant fibers. Okay, like if you eat a celery stick, it's crunchy. That crunchiness comes from the cellulose, the plant fibers. We cannot digest the fibers, but the cellulose will help us, with bowel movement, right? But from the plant's perspective, the cellulose is important for structural support. Structural support. Last but not least, we have something called chitin. And you will find chitin in the exoskeleton, like the outer shell of insect, right? Or crustacean. These are like crabs, lobster, right? Like shelled animals, right? And the function is structural support as well. Okay. So there you have it. Those are the 4 types of carbohydrates in the body. Let's do a few poll questions. There we go. Yeah, most of you got it right. We wrote it down earlier, right? If you take the glucose and you combine it with fructose, you get your kitchen sugar, which is the sucrose. Now, next one is a little bit wordy. Take some reading, and this would be an example of a multi-select question. You have to select all the false statements. So go ahead and give that a try. All right, that was 1.5 minutes. We're gonna end the poll, share the result. So A, B, C seems like popular choice. Someone chose F, not sure why. But let's go through each one of them. We're looking for the false statement, the wrong ones. So first one, polysaccharides are important both for energy storage and to provide structure to cells. So for energy storage, we have things like starch or glycogen. And for structure, we have things like chitin and cellulose. Right? So that's a true statement. We are looking for the false one. So we are not going to select that. Glycogen is important both for energy storage and to provide structure for cell. That is incorrect. That's the false one. That's why I'm circling it. Glycogen is only for energy storage, not for structure. Cellulose is found only in animals. That is not true. Cellulose is found in plants. Sorry, did someone have a question?
No, just I said in bland, it's false.
Oh, yeah. Okay, thank you. Glucose, fructose, and galactose are examples of monosaccharides. That's true. We listed it out in the table, right? So that's not the answer. And finally, starch is a storage polysaccharide made by plant cells. That is also correct. So the ones that you should be choosing would be B and C. Those are the false ones. Okay. Next one is about lipid. We will come back to it after we do lipids. Okay, we gotta skip the break today. Okay, I'm sorry about that because we just there's so much to go through in lecture 2. We might not have enough time if we do have a break. So next one is lipids. Now I gotta write a little note here for you. Lipids are a little different from the other macromolecule because lipids are not made up of monomers. Okay. Instead, lipids have components. Okay, or sometimes they're called like subunits. Okay, so no monomers. It's not like a long chain of something, but more like, you know, different components coming together to form the molecule. So we have different types of lipids here. The first one is fat, okay, or triglyceride. That's the fancy name for fat. And there are different components in the fat molecule. There is this part of the molecule, right? That is called the, let's take that away. That is called the glycerol. And in addition to the glycerol, we have 1, 2, and 3 of these things. Those are called fatty acids. Okay, so 1 glycerol plus 3 fatty acids. Okay, these are like CH and repeated many, many times. That's what makes up fat. What's the function of fat? Fat is actually very useful for storing energy as well.
And providing insulation.
So we store energy as glycogen, but then fat is for like long-term storage. Okay. And someone said it's good for insulation, right? And protection of organs. Right? It's not uncommon to have a little bit of fat around key organs, your liver, your kidneys, your heart. Those fats will insulate it, meaning it will keep them warm. It will protect it, cushions it a little bit. But of course, you don't want to have too much, right? Too much is going to interfere with the normal functioning of the organ. Okay, we have another lipid molecule here. This is a phospholipid. Okay, so let's check out its component. We have the same part as the fat. We have the one glycerol. Over here, we have two fatty acids. And we also have what we call a phosphate group. Okay. Did you learn this in chemistry yet? Like, did you know like PO4 is phosphate? Maybe. Okay. So phospholipid, usually we draw it like this. Okay, we'll talk more about phospholipid next class perhaps, or the next class. We draw it like this, and it's a very special molecule because it has two opposite ends. The head that's made up of the phospholipid, we call it the hydrophilic head. Okay, that's the part that will interact well with water. And then the fatty acids, that would be the hydrophobic tails. Okay, so one part binds well with water, the other part will try to move away from water. That gives it a very special property, which actually makes it perfect to be a major component, major cell membrane component. Okay. Your cell membrane is made up of two rows of these things. More on that next class. Okay, last but not least, what is this thing? Does anybody recognize what this might be?
A steroid?
That is a steroid. That's right. Very good. And you know, we need steroids in the body for hormones. A lot of are, well, not all the hormones in the body are made of lipids. A lot of them are protein based, but some hormones are steroid based. This is steroid. And for steroid, the component, let's use a color that we haven't used yet, maybe orange. The components include these carbon rings. Okay, so we have 4 fused means they're stuck together. Carbon rings. And that's the core structure. And on top of the carbon rings, you are going to have some of these accessories. Okay. These are called functional groups. Functional groups. Depending on the kind of functional groups you have, it's going to give it as different properties. Okay, so some functional groups are like OH, other functional groups is like hydrocarbons. We're not going to bother ourselves with all the details. Just suffice to know it's the 4 fused rings with various things stuck to it. Okay, so they form hormones. Form hormones such as what kind of example did I give you guys in class? What kind of hormones in the body is a steroid hormone? Male hormone, female hormones? What's the main male hormone? Anybody know? Starts with a T.
Testosterone.
Yeah, that's
And
right,
estrogen.
testosterone.
And
And for
estrogen.
female is estrogen, right? Estrogen, progesterone, right? These are all steroid hormone. Okay. So there you have it. Any question about any of these things?
Yes, I have a question.
Mhm.
I was thinking wax is among type of lipids.
Yeah, we talk about wax as well in the class, but these are the three you should focus on, okay?
Okay.
Mhm. Wax would form like water repelling surfaces, like the beeswax, the wax that you found on the surface of apples, for example. Okay, next we have another chart that compares the saturated fat with the unsaturated fat. All right. So what's the difference? Well, for saturated fat, it is made up of 1 glycerol plus 3 fatty acids. 3 fatty acids. Okay. And the type of fatty acids that you have here would be saturated fatty acids. All of them. Okay. And what does it mean to have saturated fatty acids, you ask? Well, saturated fatty acid means there are no double bonds. No double bonds, no kinks. Okay. And the carbons are bonded to maximum number of hydrogen atoms. You cannot fit any more hydrogens onto the carbons. They are saturated with hydrogens. That's why they're called saturated fat, okay? Let's take a look at the unsaturated fat. 1 glycerol plus also 3 fatty acids. And in this case, at least 1 fatty acid is unsaturated. Okay. What does it mean? Right. It might have 1 or more double bond. Okay. 1 or more double bond and kinks. I'll show you what it means in a bit, okay, with the kinks. And then some carbon is not bound to max number of hydrogen. Okay. So if I have to draw the saturated fat, you would have the glycerol. You would have the glycerol, and then you would have 3 fatty acids, and none of the fatty acids have kinks in it. For the unsaturated fat, at least one of them is unsaturated, and the unsaturated one might create a little bend, a little kink in it because of the double bond. Okay, so take a look at the pictures in the PowerPoints, and you will see what a double bond looks like. Okay, it's also possible to have more than 1 kinks, right? Because there are more than 1 fatty acid, unsaturated fatty acids. So if they are saturated fat without the kinks sticking all over the place, you can pack them really closely together. And for that reason, the saturated fats, they would be solid at room temperature. Whereas the unsaturated fat, because of all these kinks, all these bands that are sticking out all over the place, the molecules can get really close to each other, right? So they stay quite far apart compared to the saturated one, and that makes them liquid at room temperature. So natural sources of saturated fat, they are mostly animal derived fats. So actual examples of saturated fat. Anybody have an example for me, actually? You might have this in your home again. Saturated fat.
Butter.
Butter, that's right. Anything else? Lard, right? That's another one. Some people like, if you use lard to make, especially if you want to make like the fluffy pastry, right? Adding a little bit of lard is gonna give you that, fluffiness, right? In your pastry. Super unhealthy though, of course. What about unsaturated fat? These are usually plant derived, usually, okay, not always. Like coconut oil, it's saturated, even though it's derived from plants, right? Okay, but any examples of unsaturated fat before we move on? Just like maybe give me one.
Olive.
Two. Yep, olive oil, right?
Nuts.
Peanuts.
Yeah, peanut oil, canola oil, avocado oil, grapeseed oil, like basically all those liquidy oil that you use for cooking, those are plant derived. Okay,
Seeds.
what's that?
Seeds.
Yeah, seeds, right? It's seed oil, right? Grapeseed oil. Very good. That's that. Okay, that is it for the lipid. Okay. Let's fill in more stuff first, and if we have time, we'll do more polls, okay? Next is proteins. Okay, so here we have an amino acid. Amino acid is the monomer for proteins. So the amino acid has several key features to it. There is a central atom in all of them. The NH2 here, this is called an amino group. And over here, we have what's called the carboxyl group. Carboxylic acid. And then we have a side chain down at the bottom. Side chain. I'm going to show you some amino acid here. Right, these are all amino acids, and depending on which side chain they have, they could be grouped into different categories. Some are polar, some are charged, some are, negatively charged, and then some of them are polar, some of them are non-polar. Okay, so you can see all of them has the carbon in the middle. All of them has the carboxylic acid group and the amino group, right? It is the side chain that distinguish them. And there are a total of 20 amino acids that exist. Okay. So what we do here is we can take the OH from one, take the H from the other, and we will remove the H2O, and then we'll form a new bond. Right? The new bond will connect the C over here with the N, and this new bond has a name. It is called a peptide bond. Okay, it connects them together. So this could go on repeatedly. And I'm just going to draw it out to show you. You don't have to draw it now. You can just watch and try to do it later. So we have central carbon and a hydrogen, and we have the NH2 over here, and then we have side chain number 1. Okay. And then we have the C double bond O
Miss Vincent, I cannot hear you.
Hi, can you guys hear me now?
Yes, yes.
Oh, sorry. How long was
Yes,
that out
yes.
for? When did you
First
guys
double
know?
bond O,
The double bond? Oh, okay, yeah, okay.
the
So
first one.
all right. I was just showing you like how these are being repeated, right? And so like I can draw another one here, R4. Okay. Like you know, I'm not gonna ask you to draw this, okay? But I'm trying to show you that you can keep on linking it together repeatedly, right? And you might be able to see here, right? That like that's like amino acid number 1. Over here, that would be amino acid number 2, amino acid number 3, and then amino acid number 4, right? And then it could just keep on repeating itself, right? Endlessly. Right? So some proteins are really long. Some proteins are hundreds of amino acids long. Some are even thousands of amino acids long. Okay. And what you see here is, you know, the backbone does not change. We have the NC C double bond O, and then NC C double bond O, and C double bond O, same thing, right? And this just keeps on repeating itself. And we call this here, this whole thing that keeps on repeating itself, that's called a peptide backbone. Okay, and then all these things are on the side, right? That's a side chain, right? They might be the same, it might be different. It doesn't really matter. What matters is you connect them together to get your protein. Okay. All right, moving on. Complete the table about proteins. So in proteins, we have C, H, O, and N, and then traces of sulfur. Okay, a little bit of sulfur. It turns out one of the 20 amino acids, one of them has sulfur in it. And so the building blocks would be 20 different amino acids. Now, what do we need proteins for? We need proteins for hormones. Okay, some hormones are lipid-based, like the sex hormone, testosterone, estrogen. But a lot of hormones are protein-based, such as insulin. You probably have heard of that, right? It helps you absorb sugar. We also need proteins for structure. For example, muscle. A lot of proteins in muscle. You have proteins in your hair. You have proteins in your fingernails. Okay. We also use proteins as enzymes. Okay. So, for example, if we have sucrose and we want to break it down into glucose plus fructose, we are going to need an enzyme that does that in our body, right? So that would be, you know what, actually, instead of using sucrose, it's probably easier to use something that you might be able to relate to. Sorry, lactose. Okay, so lactose is glucose plus galactose, right? Okay, so to break down lactose, we would need an enzyme to do that. The name of the enzyme is lactase. Don't worry about the name. I'm just giving you as an example, right? So people who don't have lactase, people who don't have that enzyme, they won't be able to break down lactose, and they might be lactose intolerant, right? You've probably heard of that before. Okay, so every reaction in the body requires an enzyme. Now, when we talk about protein, it is important to understand the levels of organization of the proteins. Okay, so generally there are 4 levels of structure when it comes to protein. The primary structure is talking about the sequence of amino acid. So if you connect all these amino acids together, if you read it from one end to the other, that sequence, that's called a primary sequence. Remember, there are so many different amino acids, right? So maybe you connect the alanine with the valine, and then with the lysine, with the phenylalanine, so on and so forth. That whole chain, if you read it out one by one, that's called a primary sequence of the amino acid. And you know, this is determined by DNA. Okay, we'll learn that in lecture 7. Okay, so your DNA code, your genetic codes determine the sequence of amino acid, the primary structure of your protein. And what connects the amino acids together is the peptide bond that we drew just a few minutes ago, right? So then illustration, okay, it's basically like all these amino acid linked together. Okay, so the sequence is the primary structure. Now the secondary structure is the next level up, right? This deals with whether or not there are alpha helices, okay, alpha helices, or something called beta pleated sheets. Okay. And if you don't know what I'm talking about, basically this is like a noodle, okay, like a spaghetti. And then the secondary structure is taking that noodle, that spaghetti, and then some part will form these twists and coils, and then other parts will form these zigzag. Okay, so these coils, they are the alpha helices, and then these zigzags, they are beta. So depending on what kind of amino acids you connect together, sometimes there are more helices in a protein, sometimes there are more beta pleated sheets. You don't have to have both, right? The entire protein can consist of, you know, only helices and no sheets, or vice versa. Okay, so what's holding these you know, loops and zigzags together? They are held together by hydrogen bonds. Remember we talked about hydrogen bonds earlier today, right? You get hydrogen bonds when a slightly positive part of a molecule is interacting with a slightly negative portion of another molecule, right? Okay, such as like 2 water molecules can form hydrogen bonds. Well, hydrogen bonds can form from the backbone as well. So hydrogen bonds are formed in the peptide backbone. Remember the peptide backbone, right? This is the like this one, right? The one that keeps on repeating itself, right? Okay, so like the oxygen here is slightly negative, and the hydrogen here is slightly positive. So, you know, those could loop back on itself and interact and form hydrogen bonds. And those hydrogen bonds will be able to hold the helices together. Okay, now if we go one level higher, then we have the overall 3-dimensional shape of the protein. Okay, so this will fold up on itself, right, and become like a blob. Okay, so like, you know, you still have your helices, but maybe it folds back on itself and have the zigzag like on top of the helices. And the point is it creates like a 3-dimensional structure with a specific shape. And what's holding it together would be the interactions between side chains. Okay, and there are different kinds of interactions. You should look back into your PowerPoint slides. Some interactions would be, you know, ionic bond holding them together. Other interactions would be hydrogen bonds. right? We have what's called hydrophobic interactions. So take a look at that in your PowerPoint slides. A lot of proteins will stop at the tertiary level, but some proteins will move one level higher into the quaternary structure. Okay, so quaternary structure occurs when 2 or more polypeptide proteins join together to form a complex. Okay. And this would be held together by interactions between polypeptides. Okay, so in class, I gave you an example called hemoglobin. That's a molecule that carries oxygen for you in the body. And that has like two purple ones, for example, and 2 pink ones. So a total of 4 different proteins, but they come together to form one big complex. Okay, this is protein 1, protein 2, 3, 4, and you form a complex. And so these are the 4 levels of protein structure. Anyone have any questions? Okay. We're going to move on to the last one, which is the nucleic acid. So,
I'm
yeah,
sorry, Vincent.
no problem. Go ahead.
I'm not really sure I understand this the structures. Could you briefly go through the tertiary and quaternary structures again, please?
Sure, no problem. Okay. So let me see if I can grab a piece of prop here. Okay. So like, you know, a piece of paper is 2D, right? Okay, it's just flat. Right. So like if I draw my let me get a Sharpie here. If I draw on here, can you even see that actually? Let me see if we can draw that. See that. Okay, so this chain right here, right? That's still flat, right? And then if you go through the amino acid order from one end to the other and you read it all out, that's your primary structure. Now this is going to coiled up. Okay, I'm gonna draw it first and then I'm gonna show you. Okay, like that, right? It's gonna have some parts. Can you even see that? Probably a little bit, right?
Yes,
Yeah,
yes, I can.
Yeah, so you can see some parts are zigzag, some parts are coil like that, right? Okay, but for the most part, this is still 2-dimension because it still exists on the piece of paper, right? Okay, it's not 3D, right? It's not like a ball.
Okay.
Yeah, and then it will fold up, right, and become like an overall 3D shape. Okay, so this particular shape is going to be related to the protein function, and you know it's become like a ball now, and what's holding it together would be the interaction between the side chains.
Oh, that makes sense.
Yeah, okay. So then the quaternary structure is not just one ball. Now imagine I have like
It's
4 of these.
multiple.
Exactly.
Okay.
We're coming together and form like a machine almost, right? With different components working together.
Yeah, that makes sense. Thanks.
Yeah, no problem. So that is that. Okay, nucleic acid. That is the last one that we're gonna go through. The elements that are involved in the nucleic acid, basically all the key elements that are found in a living organism. So we have some C, H, O, and as well as phosphorus. The building blocks of nucleic acid is going to be a nucleotide. So there are different types of nucleotides, and I'll explain what those are in a bit. And for biological functions, the nucleic acid is responsible for encoding instruction to make proteins. right? And it is also the hereditary information. It's the information that gets passed on to future generations, right? We're going to have a whole lesson on nucleic acid later on. But for now, that's basically what it is. Now let's take a closer look at the nucleotide, the building blocks of nucleic acid. And so here is a nucleotide. The nucleotide has 3 parts to it. Okay, there is the phosphate group again. It's the same phosphate group that you saw in phospholipid. Phosphate group. And it is connected to a sugar. Right here, that's a sugar. Now, this sugar might be ribose for RNA, or it might be deoxyribose for DNA. Okay, after all, that's what the D stands for in DNA. It's the deoxyribose nucleic acid, whereas R is the ribose nucleic acid. Okay, it's the same sugar, but you know, it's missing an O for DNA, and then it's you know, having an extra O in RNA. And then we have a nitrogen base here. Nitrogen base. Okay. So for DNA, the nitrogen base could be A, C, G, or T. I'll tell you what they stand for in a bit. And if it's an RNA, it's A, C, G, or U. There's no T in RNA. So that's what a nucleotide is. So these are all the possible bases and what they stand for. And I know it's not terribly clear in this picture what the writings are, but it's in your notes. So C is cytosine, T is thymine, uracil, adenine, and guanine. Okay. And so some of them has one single ring in their structure. These ones, we call them pyrimidine. And on the other hand, these ones that have double rings in them, we call them purines. Okay. And the purines will always pair with a pyrimidine in the DNA. So if you think about the DNA, which is a long double strand molecule, right? You will always have a purine pairing with a pyrimidine. And the purpose, and listen carefully, the purpose of that is so that you can maintain a constant width across the DNA. Right? So like pyrimidine has one ring, right? So one ring, and then you pair it with like a 2-ring structure. Okay, maybe you have a 2-ring structure here, then you pair it with a 1-ring structure. So if you do that along the entire length, then across the DNA strand, it will always be 3 rings wide, right? 3 rings wide. Okay, so the pairing rule goes like this. Pairing rule. Right. A always pairs with T, and C always pairs with G. So to remember the purines, you can remember the following phrase. Where is my blue pen? Pure as gold. Okay, so purines, adenine, and guanine. Everything else is pyrimidine, okay? It's also worth noting that A and T, there are 2 hydrogen bonds holding them together. 2 hydrogen bonds holding them together. But for C and G, there are 3 hydrogen bonds holding them together. So it's harder to pull apart C and G compared to A and T. Okay, think about like, yeah, I don't know, having two pieces of wood, hammering two hammers, holding them together versus two nails, holding them together versus three nails. It's going to be harder to pull apart, right? If you have three nails. That's what the hydrogen bonds are. And so the more CGs you have, the more difficult it would be to separate the DNA strand. And that has implication, which we'll discuss later on. Okay. So the last part here, compare DNA and RNA. The nucleotides that we talked about, the DNA has, again, phosphate group plus the deoxyribose, the sugar missing an oxygen, and then plus nitrogen base. And the base could be A, C, G, or T. And the strand would be a double strand. On the other hand, the RNA, we also have the same stuff. Phosphate plus ribose now. And nitrogen base. And we have A, C, G, or U. So no thymine. It is being replaced by uracil. And this is a single strand. Okay, so DNA is, you've probably seen this before. It is a two strands that are twisted together, forms like the twisted leather. But for RNA, it's just a single strand with the base on the side. Okay, like that. So that's it. For the long answer question, I'll post the answers and you can look at it yourself and you know, compare the answers. There are some application questions here. Let's take a look at the first one. In a certain species of animal, 30% of bases in its DNA are adenine. Find the percentage of the other base. Okay. So what does A pairs with? You guys remember?
With T.
With T, that's right. So because A pairs with T, the amount of A in any organisms will equal to the amount of T in the DNA. So if you have 30% A, you will have 30% thymine as well. Okay, so if you add these together, that makes up 60% of all the nucleotides. Which means 100 minus 60 would give you the 40%. Right? The remaining 40% is a combination of C as well as G. Since cytosine equals to guanine, it will be 40 divided by 2. So that's 20% and 20%. Okay. Does changing the primary structure of a protein always have an effect on the shape of the protein? Justify your answer. The short answer is no, not necessarily. Because if you change the primary structure, it means you are changing the amino acid sequence, right? But let's take a look at our amino acid here, right? The amino acids are grouped together based on their properties. So let's say I have a glycine, which has a side chain of H. If you change it to an alanine, which also has a non-polar side chain, right? It's very similar. Then maybe you're not going to change the overall shape, right? Because the two amino acids, the before and after, are so similar. It would be a different story if you change it from glycine to, say, lysine, right? first of all, the side chain looks very different, and more so, you are changing from one category to another category, right? So that could completely change the property of your protein, completely change the structure. Right? So it all depends on what kind of changes you're making. All right, we will learn a lot about these kind of changes later on in the course in lecture 7. Your digestive system uses many, sorry, that's a typo, many enzymes that breaks down polymers in your food down to monomers before absorbing them. Enzyme names often end with suffix ase. For example, lactose are broken down by lactase. A generic name for these enzymes is hydrolase. Explain what is the basis of such name. Well, this is not too difficult, because you might remember earlier today we said when you have a polymer and you want to break it down into monomer, right? Monomer. This is called hydrolysis, right? So if an enzyme does hydrolysis, then we call them hydrolase. Right? Of course, there are different kinds of hydrolases depending on what kind of polymers you're breaking down, right? So if you break down lactose, you have lactase. If you break down maltose, you would have a maltase, right? You will have proteases, lipase, so on and so forth. But generally, they use the same mechanism. They add water to your chain, and it breaks them up into little pieces. Okay, I probably will have to go over like a couple minutes, but I do want to go through the remaining poll questions with you. If you have to go, then by all means, you can check the recordings later on. But if you can stick around for a couple more minutes, please do so. So let's go ahead and do these polls. Okay. Most people chose triglyceride. That would be correct. Phospholipid is glycerol, 2 fatty acids, and a phosphate head. Steroid is the 4 carbon rings. Trans fat is it's something that you get when you try to convert saturated fat into unsaturated fat. Right? So the correct answer is the triglyceride. Okay, let's take a look at this one. Like, are some of you not able to see the polls? Is that why people are not participating? I'm just curious. I mean, this is a great way for you to learn as well, right? To see if you get the right answer or not. The polls are anonymous, like, so please choose something if you could. So false about lipids. Let's see. Steroids has at least 1 fatty acid tail. That is the incorrect one, right? Okay. Steroids don't have fatty acid tail necessarily, right? They have the 4 carbon rings, and everything else here is correct. A lot of people chose D. Cholesterol is a steroid. it's in fact the base steroid that we use to make our hormones. Okay, like the testosterone and estrogen that we talked about. Okay, let's try another one.
So this question, Vincent, will be chapter will be in next Monday quiz, right?
That's right. The quiz will include all of last week and this week's material.
Okay, 1 and 2. Okay, thank you.
Yep. All right, let's take a look here. The peptide bond forms between which groups? So in our notes here, right, we can see that the peptide bond connects the carboxylic acid or the carboxyl group with the amino group, right? It's nothing to do with the side chain. Okay? It's just the carboxyl group connected to the amino group. So the correct answer for this is C. Okay, carboxyl means carboxylic acid. Some of these questions might show up on your quiz, right? So please do review them and on your own time. We have a couple more. This one should be pretty straightforward. Okay. I'm a little bit surprised by the response here, but that's okay. I guess we can talk more about it. Hemoglobin is an important protein that is composed of 4 polypeptide chains. So this is the key phrase here, right? 4 polypeptide chains, not just one thing, but 4 blobs together, right? So if you have multiple blobs coming together to form a complex, what level would this be? Quaternary, okay? Anytime you have more than one polypeptides coming together, quaternary. Level 4. Okay, another one. Okay, let's see how we approach this question. Pancreatic cells make insulin, which is a type of protein. You don't have to know what pancreatic cells are. You don't even have to know what insulin is. What you do have to know, based on the question, is that it makes protein, okay? So these cells use something in order to make insulin by what process? Because we are making proteins, right? So what's the raw material for making proteins? What's the monomers for proteins, in other words? It's amino acid, right?
Amino acids.
Yeah, so that's why this is the choice, right? Nucleotide is for making DNA, right? Fatty acid is for making lipids. That's for making sugar. So that's why it's amino acids. And when we connect the amino acid together, right, we use the process of dehydration synthesis. Okay, so the answer is E. We still have a couple more, but I think I'm just gonna actually, you know what? I don't. You should probably try it. Okay, and again, if you have to go, then go. Not gonna hold you back. Okay. Okay, again, thank you for participating. For those of you who have answered, we're looking for the false statement here. The primary structure of protein is determined by the amino acid sequence. That's correct. Examples of secondary structure includes the alpha helix, that's the little loop, and the beta pleated sheets, that's the zigzag. So that's correct. Tertiary structures are stabilized by hydrogen bonds of the peptide backbone. That is the incorrect one. Okay, if you take a look at the note that we wrote down, the where is it? Over here, right? The tertiary structure is stabilized by interaction between the side chains. Okay, the interaction between the backbone, that's for stabilizing the secondary structure. Okay, so that's why C is the incorrect one. And when you increase the temperature, that will break down the secondary and tertiary structure, but not the primary structure. That's because the primary structure is covalent bond. You can heat things up and break down the covalent bonds, right? Okay, that's the answer for C. I'm just going to go through the other two with you. Which of the following is true regarding purines? Okay, so let's just, think back what we said about purines. Right? Nucleotides can be purines or pyrimidines, right? So what are the purines? Let's just write it down first before we look at the choices. Do you remember the phrase I told you to remember? Right? What are the examples of purines?
Pure as gold.
Yeah, pure as gold, right? So A and G, those are the
Pure as-
purines. Exactly. And so let's take a look. Adenine's bonding to thymine is stronger than guanine's to cytosine. I wrote this down for you. Between A and T, there are 2 bonds, but between C and G, there are 3 bonds, right? So that is not true. That is not true. Okay, it's the other way around. Cytosine is a purine. So purine is A or G, so not cytosine. That's not true as well. Purine binds readily to deoxyribose, but not ribose. No, both DNA and RNA, they have purines, right? It's the difference between the T and the U, right? So that's not correct. Both adenine and thymines are purine. That's also not true. We can see that here. Purines have double ring structure. That's the correct one. Okay, purine has 2 rings. Pyrimidine has 1 ring. So that would be the correct answer. Which of the following is not a feature of DNA? Select all correct answers. Nucleotides within a single strand are connected by covalent bond. That is correct, right? All the macromolecules, the monomers are connected through covalent bond. So that's correct. We are looking for the NAT feature. Adenine forms base pair with uracil. That is not correct. Okay, not correct because there are no uracil in DNA, right? So only thymine. Complementary strands are held together by hydrogen bonds between phosphate groups. Not true. Not the phosphate group. It's the nitrogen base. Complementary strands are anti-parallel and run in opposite direction. I didn't mention this in the tutorial, but this was mentioned in the lecture notes. Okay, anti-parallel means they run in opposite direction. Okay, one is upside down relative to the other. So the correct answers are B and D. Okay, this one is probably require a little bit of thinking. I'll explain to you what's going on, and hopefully when you revisit it, it will make sense. A chemical reaction occurs slowly at 37 degrees Celsius. When molecule X is added, the reaction speeds up significantly. Which of the following is a monomer of molecule X? So what do we add to a reaction that causes it to go faster?
Catalyst.
Yes, but a biological catalyst is called what?
Enzyme.
An enzyme.
That's right. And what are enzymes made up of? Like, is it a carbohydrate, protein, nucleic acid, lipid? What is it? Anybody remember that?
Protein.
Yes, enzymes are proteins, right? These are proteins. And so they are asking which of the following is the monomer for molecule X, for proteins, essentially. So we know proteins are made up of amino acids. And so that's the answer. That's what amino acid looks like, right? This is a nucleotide. This is a sugar. And that's a fatty acid. None of these would work. This is the amino acid that makes up the protein. Okay. Now, a couple of things. Okay, I know some of you probably are a little bit concerned, right? You look at these questions and you're like, oh, they are so hard. Is that what to expect on the test? Yes and no. Okay, so some questions will be hard like these ones, but not hard because like it's possible or something, right? Like, it will require you to think quite a bit. It's not straightforward answers, right? But some of them will be like this. But there will also be quite a lot of questions where it's like straightforward like something like this, right? Something that you can just quickly look up, right? And you would know the answer without thinking too much, right? Okay, so it would be a combination of these questions. When I do these poll questions, I want to do the harder ones with you, right? If I do all the easy ones, then you might get a wrong idea. We're like, oh, the quiz is so easy, I don't have to study, right? But keep in mind, there are some of these harder questions as well as the easy questions. And if you're a little bit lost today with the session, it's probably because you didn't watch all the recordings. Okay, so I know I said this already, and I don't want to sound like I'm nagging you, but you must, in order to do well in the course, you must do your part and watch the recordings. Okay, ideally before coming to the tutorial, if not, definitely afterwards as well. Okay, so thank you for staying for extra 15 minutes. I do appreciate your patience. And if you have any question about the quiz between now and Monday, please feel free to email me and I will help you out as best as I could. All right, I will see you all next Wednesday for our next live session. Okay?
Okay, Vincent,
Bye.
please, may I speak to you?
Yeah, I'll talk to you. Just hang tight.
Thank you.
When other students leave, I'll talk to you. Okay?